Welcome everybody to Lecture 2, Databases and Information Systems in the winter semester 23-24. And this course can also be taken as information retrieval, and indeed is by some of you. So what we will be talking about today, about your experiences with the first exercise sheet, which was a very simple implementation of the inverted index, the basic data structure behind all search engine. Say something about your tutor feedback time slots for those of you who do the exercises. And today we will talk about ranking, and you will see what that is in a second. And the exercise sheet will be to implement it, and we will also talk about this. And there will also be a small competition. So first some excerpts from your feedback. So most of you liked it. As usually, programming was a little rusty for some, but you're getting back into this. Here are some excerpts, very nice sheet. All the contents needed was well explained. Good and welcoming introduction. Sheet was kept simple. Yes, it was deliberately kept simple. I think it was a pretty cool sheet, not too hard, not too easy. Lecture was easy to understand and follow. I'm looking forward to the rest of it. I've not coded in Python in quite some time, so quite a few people wrote that, but in a positive sense, like I'm getting back used to it again. After a long break, need to get used to coding again. Some people also did the optional parts, which is great, so like the highlighting. Of course, that takes time. I invested more time than I like to admit. We were surprised by this, so there are over 300 registrations for this course, and around 80 people, I think, submitted a sheet. That's interesting, less than we expected for the first sheet, but interesting, yeah. And also interesting, usually there are about 20% of people who say for the first sheet that, oh, it's too hard or everything. We didn't get any such comment this time. I guess those people just didn't commit a sheet in case they are here. So the sheet was about a very simple search engine, our movie collection, and then let me just show you the master solution here, which is also linked on the wiki. So this now just reads and maybe before I show the master solution, it's maybe a good idea to show the data file again. This was the input file. It was just a collection of movies. Let me even put, and it was ordered by IMDb rank. So about here we have the line numbers, 150,000 movies, title, description, and then some additional information which you don't need for this sheet, maybe for later sheets. So that was the input, and this is what you were supposed to write, a program where you can just give this input file or any input file as an argument, and then you can type your keyword query. So here were some examples that worked well, and let's just very briefly go through these examples, positive and negative, and why they worked or didn't work well. Godfather, what would you expect? The 3 Godfather movies, and you get the 3 Godfather movies. Godfather 1, 2, and 3, with Al Pacino, Francis Ford Coppola movie. Why does it work? Godfather is not super specific. There will be other movies containing it, but the movies which you expect are the most popular ones, so it works. Tarantino is another example. You expect movies by Quentin Tarantino. You only get movies by Quentin Tarantino. Why? Because this word is so specific. If it matches, it's the director. Zombie. So I deliberately chose examples which are different in kind. What you expect, probably zombie movies, and you get zombie movies, because if somebody mentions the word zombie, it's probably a zombie movies. Lord Rings is also interesting. Let's type it, Lord Rings, and you get Lord of the Rings. That's a bit different than the other one. Lord is very unspecific. Rings is also very unspecific, but it's a very popular movie, so you get the expected movies first. So this one, romantic comedy, let's try that. This is an example of a movie that didn't work very well. It does, so sometimes you have movies where it says romantic comedy, but first is American Beauty, which is kind of a comedy. It has comedy here, romantic here, so there are some romantic elements, some comedy elements. It's not really romantic comedy. So here it was important that the words are not close together. Titanic. You would expect the movie Titanic first, of course, but you don't get it first because there are other movies which are more popular which mention Titanic. So many interesting things you have to consider. And that was the whole point of the exercise. You think, oh, that should work, that's a good idea. And when you try it, you see, oh, it doesn't work. Interesting. So that's very typical for this kind of research. You have some ideas, some expectation, then you try it, and then you see all kinds of effects why it doesn't work. 2006 film. You would expect 2000 films from 2006, but you don't get, or if you even just type 2006, you get 0 hits because we didn't index any numbers. Very simple, but of course important. And that's the last one, Spider-Man. You would expect Spider-Man movies, but you don't get the Spider-Man movies because the Spider-Man movies, I think, contain it with a hyphen. And now you again get movies which just refer to Spider-Man and not about Spider-Man. So many different effects, why it works or doesn't work. So that's an interesting slide, I guess. And of course, there are many more different phenomena. Okay, before we move on to the content, one more organizational thing. So you will get a tutor. If you have asked for feedback, if you have submitted the sheet, number 1, and then you should ask for feedback. And it's very nice, you wrote very diverse things. Some people said, I'm fine, just let me know how many points this is worth. Others said, please give me detailed feedback. Others wrote, give me feedback on this, please, not on this. That's very good for us because then we can focus on our effort on where it's needed. So if you asked for feedback, you will find it in your repository in a file feedback tutor.md and you get it by doing SVN update. Then you get the latest version of the repository from us. How do you know when you should do SVN update? Well, you could do it every minute. Actually, I'm not sure. I think some tutors, or maybe we will ask our tutors to just write you an email or something. Did we do that in the past, Sebastian? Maybe that's a good idea, right? That you get a message, your feedback is there, and then you know SVN update, and I get it. We introduced this, I think, 2 years ago. So we have the forum. We don't have tutorials for the reasons I explained in detail in the last lecture. I will not repeat it. But for some people, the forum is not enough. They need kind of individual help for all kinds of reasons. And we realized that. That's why we have a tool, which I briefly show you here, where you can just book time slots with your tutor. So here, one tutor is missing because he just became a father, but he will be with us again next week. So let's say Patrick Brosi is your tutor, and you will see this in Daphne, who is your tutor. So you have some slots here, and that's up to the tutor to say which time slots they have. It's short time slots. If you need more time, then you can ask for that in this short meeting. You just write your email. So very easy, very low barrier way to get a short meeting and ask all kinds of questions. And the link is on the wiki. So who is your tutor? That assignment will be made hopefully today. If sometimes there are technical problems, then it will happen by tomorrow. And since it's totally up to you who submits, who doesn't submit, you can make up your mind every week again from scratch. There may be imbalances, so some tutors might end up with 20 students, another one has only 5 students, so we will shuffle around students, which means that your tutor may change over the course of the semester. It might not, just so that you know. Any questions about that before I move on to the contents? Or any questions about anything? No questions. I continue. So today is about a ranking. So let's first say why we talk about ranking. So, very simple thing to understand, but let me just say it, although it's obvious. When I type 2006 here, what does it mean? It's what do I search for? I have a search desire in the back of my mind, and I express it in keywords. So maybe now I want to find movies from the year 2006, but I didn't write that. So you have to distinguish between the search desire and the query, and that's what makes search hard always for all information systems, also in databases and other systems. So there is what you actually want, and then what you type. And so naturally, and we have seen examples for that, you type your query and then you get stuff where you say, yeah, this is what I was looking for, and you get stuff where you say, this is not what I was looking for. And the important word here, which is used in this context, is relevant. So there is stuff which is what you expected and stuff which you didn't expect. And you already saw this, and exercise 2 is all about this relevance. Naturally, you search and you want the most relevant ones first. And sometimes it works, sometimes it didn't. And this is especially important for web search, where, I mean, if you just get all documents which contain your query words, I mean, let's just, I don't know, if we type Star Wars here or whatever, you get one, these words are probably mentioned in a lot of documents. You have over 1 billion documents containing these words. You want the ones you're actually looking for first. Yeah, and this sounds so obvious, but all the search engines before Google did this wrong, basically. You would type a query and you would get some super irrelevant document first, which does contain the word, but it's not what you were looking for or what anybody would be looking for. So not such an easy problem. And why is it not so easy? Because you have to somehow measure what relevant means. And relevant is something which is in the mind of the person who is searching. So kind of a hard problem. And that problem we are trying to solve today. So how do we solve it? Here's the basic idea. The basic idea, let's go back to our inverted lists. Inverted list, university, in blue, I have the IDs of the documents containing university. And now I also have a score. And right now, just take this score for granted. In a second, I will explain how to compute these scores. And this score is somehow, it should say, this document, or this document, 127. Yeah, it's really about university. The word university is here for a reason. Here for 53, 0.2, it's a low score. Yeah, the document mentions the word university, but it's not really about university. So we have seen this in our examples. Maybe let's do Titanic again to make this clear. So first movie is Lord of the Rings, and it mentions Titanic. So we would give Titanic a low score in this document. Because yes, it contains Titanic, but it's not really about the movie Titanic or about the Titanic. Whereas in the document with the movie, in the movie description for Titanic should get a high score. So and we do this per word. So that's the basic ideas behind basically all search engines. So now we still have a problem. How do we compute these scores? And then, but before we will talk about that, so now I have a keyword query like before, and now I just aggregate the scores. So document 17 just contains, and note a new thing here. Now we are merging. Last time we were intersecting. Document 17 only contains Freiburg, a university, and not Freiburg. We still have it in the result list, and we just take only the score from that. Let's take another one, 53. And 53 occurs in both, contains both university and Freiburg, and then just we sum up the score. So aggregate just means you have several scores. In this case, let me just write this. in this case sum. Doesn't have to be sum, could also be a different form of, you could also take the maximum or something like that, just saying that's one way to aggregate sum. 97. 127 contains both words with a high score, so it gets 1.5, 0.8, 0.7. And then we sort this. And now 127 is first, it's the one with the highest score. Why? Because it contains both of the words with a high score. One other important thing to note, understand this, 17 contains only university, not Freiburg, but with a decently high score, 0.5. It comes before 53, which contains both of the words, but with a low score, 0.2 plus 0.1. Is smaller than 0.5. So these things can happen and do happen. So that's important to understand. For some reason, these things are called postings. These entries in the list, they are now more complex. Document ID score, they could contain even more information, like where in the documents do these words occur, and so on. Any questions about this? So that's like the basic stuff we are dealing with today. We have these inverted lists, document IDs, and now also scores. Now let's see. Okay, first of all, okay, that's just a side remark, not really needed for the exercise sheet, but I did want to mention it. You're doing the merging here, and now you have to sort it. So that's sorting. How do you sort? Well, sorting takes time n log n. It's not the topic of this lecture, where n is the number of results in your list. N can be very large for a web search engine, but when you, in a typical engine, let's say you have these 1 billion hits for Star Wars, you only want the top 10 or the top 3. So actually what you need is a partial sort, and I just wanted to mention this. So it's enough. Assume that this list here has 1 billion entries and you only want the top 3. And maybe you want to implement it for the exercise sheet, you don't have to. I just wanted to mention that partial sort, so you have a long list, you want to sort it, but you're only interested in the top k, the k largest elements. You don't need to sort the whole sequence. This can be done much, much faster. N log n, that's a lot when n is large. This is n, so you have to look at all the elements once. You have the n, but then you have k log k, which is very small. So it's essentially linear. And for those who are interested, I'm just mentioning this on the side. You can do it with k rounds of heap sort. Heap uses a binary heap. You learn that in algorithms and data structures. You can also do it with quick sort, where you don't recurse when it's outside the range of results you're interested in. You can modify many sorting algorithms so that they just give you the top k. You don't have to do this, but maybe you have spare energy, you're interested in this, feel free to do it. And most programming languages, except Python, which is not about efficiency, have functions for this in their library. So, how do we compute back to the scores, meaningful scores? So where do these numbers come from? They are obviously very important, kind of reduced our initial problem to computing these numbers. And I already explained it, this number should somehow reflect, so how do I manage this, that Titanic gets a low score here? How do I do this? That's what we want. And the problem is, it's kind of subjective, or kind of you have to, it looks like you have to understand, right? I have to understand, oh, this document is really about Lord of the Rings and not about Titanic. So Titanic should get a low score. So we need artificial general intelligence, it looks like. And it has been looking like that for 70 years. And today we will not yet do artificial general intelligence. We will do it in the next lecture or in a later lecture. We will do it in a very simple way, which has been the way it has been done for decades now. There's a shift now. And here's a very basic idea, which is still used a lot, term frequency. Let's just look how frequent the word occurs. It's a very simple proxy heuristic. You say, oh, this is a long document. It only contains Titanic once. Probably Titanic is not so important for this document. I just count how often the document occurs here. Let's maybe, what was another movie? I don't know. Let's look for James Bond. Yeah, look at this. Skyfall, James Bond, James Bond, James Bond, Bond, James Bond. It's mentioned many times. So if a document is really about a certain word, the word occurs there many times. Kind of obvious idea. Here's a problem with that simple approach. And we are going to solve that problem on the next slide. Let's assume our query is University of Freiburg. Here are our posting list, document ID and scores. In blue, I have the document IDs, and here I just highlighted two documents, document 57 and 123. Document 57 contains university 5 times, the word of, the very important word of, 14 times, and the word Freiburg 3 times. And here we have another document with these numbers. Now let's do the math, how I explained it. What do we get? 57 gets a score of 22, and 123 gets a score of 26, which means this will be ranked higher, right? Because the sum of these numbers is higher. That's not good, right? So why did it get higher? It contains the word of very frequently, which really says nothing, but the words which somehow carry meaning, University and Freiburg, it contains them less often. So kind of we would say, looking at this, 57 should be ranked higher because University and Freiburg are more important than of. So that's the problem. And some of you already observed that if you type word like film or and or something in they kind of distort the results. So, and you see what you're going deeper and deeper, and you find all these other problems which look hard to solve. Now, how do we tell that university is an important word and of is not important? That also sounds subjective. Actually, there's a nice way and also simple way to do this. It's called document frequency. And here it is. We just count in how many documents does a word occur. University occurs, and let's just put some, and maybe you recognize this as a power of 2. You will see in a second, just for the sake of example, why I did this. It's which power of 2? 2 to the? 4? 2 to the power of what is this? This is 2 to the power of what? Let's start here. 2 to the power of 0? It's 1024. Which power of 2 is this? 10. I agree, it's 10. Let's go back to this one. 16384, it's a power of 2. That was not 14. I agree. 14, what about this one? It's half of 1 million. That should give you a hint. This will be on the exam, things like this. You should really know your powers of 2. And you don't need a calculator for that. So 1,000 is 2 to the 10, 1 million is 2 to the 20. Around, what's this? If I tell you that I guarantee you it's a power of 2, what is it? Okay, I hear some mumbling. Was that my echo? That's an interesting effect. Maybe someone from Zoom has. Okay, we have this power of 2s. They don't have to be power of 2s, just for the... Now, the inverse document frequency is just computed as the logarithm base 2 of n over df. And let's assume we have a collection with 1 million documents, which is 2 to the 20. So we take 1 million, the next power of 2. And then we have these numbers. Let's just verify this. So IDF University, this is now log 2, and I won't do it for the other numbers, of, that's just this formula, 2 to the 20 divided by 2 to the 14, which is, 2 to the, let me just write, you should absolutely know your, and there will be a question about this in the exam. So these things you should absolutely know. That's 20 minus 14, that's how it works. It's 2 to the 6, just the law of logarithms or of powers. And I won't do it for the other two. So that's the numbers you get. Log 20, 2 to the 14, so you get 2 to the 6, and the log 2 of 2 to the 6 is 6. So that's what you get. And now let's look at these numbers and understand them. So here we have a word that's quite rare. Freiburg is very rare, just occurs in around 1,000 documents of 1 million, which means this IDF, because the DF here is in the denominator, is rather large. And the intuition is, this is a word, if it's there, it means something. It's relatively rare overall. If it's rare, it means something. It's a significant word. Of occurs in half of the documents, half of the 1 million. So we have log 2 of 2, the 2 meaning half of 1 million documents contain it. So the IDF is 1. So a very low score, which says of occurs everywhere. It's not very meaningful. University is somewhere in the middle. It's the idea behind IDF. And why do we take the log 2? We don't have to take the log 2. We would have the same effect like higher, if more specific, without the log 2. That's a very common thing to do. Look at the differences in these numbers without the log 2. They're like enormous, right? There's a difference of 500 from off to Freiburg. That's too big. We want a difference, but we don't want it to be as large. By taking the log of this funny thing, we get numbers 6, 1, 10. There's a range here, but the differences are not super large. That's what we want. And now let's just apply it and see that it works. That's our earlier example. I won't explain it again, should look familiar. Here the situation was that 123 was ranked higher because it contained the word of so often. And now let's look at the list with tf.idf scores. And let's just do the math quickly to see that. So what did we have? We had, I'm sorry, this is not what IDF. I wanted to write IDF. So the IDF of, what was the IDF of university from the previous slide? 6, that's correct. So that was like medium. The IDF of was 1, very low, yes, great. And the IDF of Freiburg was, yeah, exactly, 10. So let's just maybe write it on. So this, the 30 here is just 5 times 6, right? The 12 here is the 2 times 6, so the TF times the IDF. The 14 here is the 14 times 1. The 30 here is 3 times 10. So because Freiburg is so rare overall, the 3 gets multiplied by 10. And here we have 23 times 1. And here we have the 1 times 10. And now we do the math again. And we just sum it up. And now we get a much higher score here, because yes, of occurs very frequently, but the other two words which have a higher IDF they get more weight now. So the 74, so 57 will now be ranked before 123. So that's tf.idf, very important formula used as a heuristic in a lot of settings, not only information retrieval. Basically, whenever So that's really it's very simple to understand the principle. It's important to understand and remember this. Whenever you have objects and you somehow want to give them scores, think about tf.idf. Term frequency and also, okay, how often does this occur overall? Here's some problems with tf.idf in practice, and we will solve them now. So the IDF part is fine, can also be improved. The TF part has some problems. And let me start with an example. Let's go back to James Bond. This mentions James Bond several times. Now just this movie description is pretty long. If it would be twice as long and go on like this, it probably would contain the words twice as often, right? Just because it's twice as long. So some documents are shorter, some are longer. Longer documents will contain more words. It's kind of unfair to say that if this document would be twice the length, that it's twice as much about James Bond, just because it contains the words twice as often. That's kind of strange. Just because it's longer, it's not more about the word. And that's written on these slides. I will not... I just explained to you the intuition. You can look at this yourself at home. I just gave you the intuition. I will now tell you how to address this. So here's a formula which kind of takes into account that longer documents tend to have more words. And this is a very famous formula. It's still used today, BM25. It's called BM25 because the people were just, for decades, just randomly trying out formulas, BM1, 2, 3. It's like the programming language C, which is the successor of B. And so that's just what computer scientists do. They give things funny names. So that's the formula is tf.idf. So this should look familiar. That's the IDF part from before. Let me just write that down. But the TF part is modified. And how it's modified, I will explain now. So this is the IDF part we have seen before. And what's the TF? That's the TF modification. So we take TF, as we had before, term frequency, and we multiply it by k plus 1 divided by k times alpha plus TF. Where alpha is this. Where DL is the length of the document, and average DL is the average length of the documents in my collections. So kind of this here says this document is twice as large as the average, or is half the average size. And let's, okay, this is a strange formula, and now in the next 10 minutes or so we will try to understand this. Somebody says, here's a formula that works well. So it looks magical or strange or whatever. We now try to understand this formula. One way to understand the formula, and there are standard settings, like when you use BM25, use these settings. And it will be part of the exercise sheet to play around with these settings and see what works how well for our movie data set. But let's first understand two extreme settings and see that this formula makes some sense. And let me take the pen here. So if B, let's understand this alpha. If B is equal to 0, what is alpha? If B is equal to 0, yeah, it's just 1. Alpha is 1, so alpha is a factor which somehow takes into account how long that document is compared to the average, but there's a factor B here which says how much should we take that into account. That's a very common thing here. So it B, 1 minus B, and if the B is very small or 0, then I say, okay, ignore this correction by document length, and I just get 1. If B is 1, then this gets full weight. So in this case, B equals 0, alpha is just 1, and now our formula is just TF star. Let's write this down. Now it's just TF times, and this we will need often in the following: k plus 1 divided by k plus tf. And now let's look if also k is 0 now. What do we have? If k is 0, then I have k plus 1 is 1, k plus tf is just tf, then tf star is just tf divided by tf, which is 1. For if tf is, yeah, I should write that if, no, we should be careful here. This is not true the way I wrote it. This is this now depends whether actually, let's look at this formula. Is it even defined for tf? Is it's not really defined if tf is 0, right? Yeah, let me write that here. So k, this k parameter is greater or equal to 0. This b parameter is between 0 and 1. And for if tf is 0, tf star is just defined to be 0 as well. It's kind of a corner case of this. So, but if tf is not 0, yeah, then this is true. tf divided by tf, which is just 1, if tf is not 0. Yeah, that's pretty simple. So this kind of mathematics, you will certainly also get it in the exam, just computing with formulas. We have a little bit more on the next slide, so I just plug something in here, k equals 0, I get tf over tf, which means no matter how often the word occurs in document, tf star is just 1, which is just our binary model from the first exercise sheet, where we didn't really, from your first exercise sheet, where you didn't care how often a word occurred in the document. Now let's look at another extreme case when you pick the k very large. Let's look at that, what happens. If k is very large, so let's write it down again from the previous slide, tf star, and I should write this tf again because it's not tf star. If b is equal to 0, it's just b will be equal to 0 all the time now in the following. That's k plus 1 divided by k plus tf. Now if k goes to infinity, now k is in the numerator and the denominator. How do we compute if this goes to, what happens if this goes to infinity? Let's just divide by k in the numerator and the denominator. 1 plus k divided by 1 plus tf divided by k. So now if, let's take the limit, if k goes to infinity of this, so if this goes to infinity, then this goes to 0 and this goes to 0. So then this just becomes tf. So we have two extreme cases here. So now we already understand a bit better what the k and what the b do. So the b, if it's 0, and we will take it 0 here and on the following slide, then basically ignores the correction for document length. And the k says how much should I take into account when a word occurs more often. Here, no matter how often it occurs, the tf star will always be 1, and here it will be the full term frequency. So really, if it's twice as often, tf star will be twice the value. And here's some more properties which are important to understand. And let's just prove them. Yeah, let's see what else is on this slide. Okay, then I can see where I can write my formulas. TF, and let's in the following, yeah, let's also work with b equals to 0 here. So tf and if b equals 0, let me just write that again, then tf star is tf times k plus 1 times k plus tf. That was the formula. So if, to prove this, let's just write tf star. So we have the tf twice here. Maybe let's just have it only, what do I do, if and only if. Yeah, let me just divide by tf in the numerator and the denominator, then I get this. K plus 1 divided by k over tf plus 1. No, actually, I don't need this here. This was a mistake. It was misguided, so so this part here is always non-zero, right? So since this is almost always non-zero, tf star is 0 exactly if tf is 0. So we have that part here. Tf star increases as tf increases. That's what I wanted to do here. Let me just write it as follows. And these are typical exam questions, and you just have to do it yourself at home to really understand it, to be able to reproduce it. That's the point of this. Let me just do what I just did. This is equal to k plus 1 divided by, so I just divide by tf. It's like writing tf in the numerator. And then at the bottom I have k divided by tf plus 1. And now, let me just say this. Now I just have the tf1 here. If tf increases, then this, if this increases, then this decreases, but it's in the denominator, so this increases again. So by having the tf only once here, I see that increasing tf increases this, because it's twice in the inverse here. So that also proves this. And now let's also do this, the limit here. What happens if the term frequency becomes higher and higher? What happens with the tf star? Let's also do that. And yeah, for that, this formula will also be useful. So let me just write it like that, limit of when tf goes to infinity, and let's look at this formula here, k plus 1 divided by k divided by tf plus 1. So if you did this simple equivalent formulation of the expression, so what happens if tf goes to infinity here? What does this become? Yeah, this becomes 1. So what will be the result? K plus 1, yes. So, and this gives you a good intuition of what the k parameter, k parameter tells you, okay, no matter how often my word occurs in the document, this tf star will be at most k plus 1, and it occurs very, very often, it will approach that. So that's what the k parameter does. And kind of, that explains the point of the whole formula. So if you see this formula, you wonder, okay, why that formula? Why not another formula? What's the point of that formula? And really, the best explanation, I mean, there's a whole, there's so much literature about this, but the best explanation for this formula is you have these three very natural properties. You have tf, you want to modify it to some variant of tf. Certainly if the word does not occur at all, this should also be 0. That's very natural. We have that property. We saw it here. If the word occurs more often, then this modified measure should also increase. We have that property. And as it approaches infinity, it shouldn't grow to infinity. It should approach some fixed limit. And it also has this property. And if you want these 3 properties, that's kind of the simplest formula which does this. If I tell you, come up with a formula which has these 3 properties, you will come up with that formula. It's or something more complicated, which doesn't help. So that's BM25, and you will implement it for the exercise sheet, and I strongly recommend that you do. And BM25, there's a popular exam questions about this formula. Okay, here's another. Yeah, that part I already explained. This was just the role of the alpha. With the alpha, you can just say how much do I want to weight the average length of the document. Here's the, how do you implement it? Think about the first exercise sheet where you have, you didn't do any term frequencies yet. So first, you have to compute the inverted lists with the TF scores. And let me just go back to a slide where I see TF scores, maybe here. How do I compute these 5? Well, we already did that in the very first exercise sheet because we just appended things to the inverted list, right? I'm in a particular document and I see the word Titanic and I just appended this document ID to the inverted list for, or let's say here's university, okay. I'm in document 57. I see university for the first time. I append 57 to that inverted list. Now I see it for the second time in the code I wrote in the first lecture. I just appended it again. I appended 57 5 times. That's what I did in the first lecture. Instead, you can just have a counter which says, oh, 57 again, counter 2, 57 again, 3. So you just have a counter here, and if you see it again, you increase the counter. So with the same implementation from the very first lecture, you get the term frequencies. Okay. So we already did that implicitly. We didn't have a counter, but we just had the 57, the document ID 5 times. You didn't do it for the first lecture, but for the first exercise sheet, but now you will do it. While you're doing that, it's also very easy. You're seeing one document after the other. Let's go back to just looking at the, right? You will process one document after the other. It's very easy to just remember the size of the documents. Okay, this has, and when I say size of the document, it actually doesn't matter what you count. You could count number of characters or number of words, make your choice. I think for the sheet we recommend number of words, but it doesn't really matter. Just remember this movie description has, I don't know, 237 words. While you are doing it, easy to remember. And when you have done it for all the documents, then you also know the average document length. So you just compute that. Now you have that. So now you have your inverted lists, you have the term frequencies, and you know these document lengths and average document length. And now you can make a second pass over your inverted lists where you can just compute this number. Now you have all the information for that number. So first you just compute the inverted lists with TF scores, and now you make a pass over them. And this is important to understand, and I recommend that you do the exercise, then you understand that it actually works. Now when I do the pass a second time, I have all the information, and let's just check to compute this formula. TF, yes, that's what I've computed in my first pass. K is just a parameter. B is just a parameter. Document length, I just said it, you remembered those. Average document length, you could compute it at the end of the first pass. N is the number of documents. DF, what's DF? Well, DF, actually we did it in the first lecture, is just the length of the inverted list, right? The document frequency let's maybe go to the document frequency. I didn't say this, but let me just, where is my slide with, where I have the, here I had this number here, Freiburg, 1024. This means Freiburg occurs in 1024 documents. This is exactly the length of this list, not of this example list, but the length of this list, it's just as long as many documents contain this. And this is also what you have after the first pass, right? You just take the length of your inverted list, and then you know Freiburg occurs in so many documents. So I really recommend that you implement it, even if you don't submit it, implement it, start implementing it, because it's kind of, you could easily do way too much work here by doing many more passes over your data or wondering how should I compute this. It's actually very simple. You do one pass where you get all this information, then you do another pass. Very efficient. So that's nice. So we have a break in a few minutes, just a few. How could this be refined further? For the exercise sheet, and let me briefly show you the exercise sheet at this point. Here's the exercise sheet. So that's what I just explained. You take your own code from the first exercise sheet, or you can always take the master solutions as well, build on that. Now just modify this build from file method in the way I just explained. Make a first compute the TF scores and then PM25 scores. Then, I hope you realized that we did something different. In the first lecture we did intersect, only documents which contain all the words. Now we do merging. We also consider documents that just contain some of the words. The exact same algorithm with a very small modification can also do merging. This zipper algorithm which goes through the list. And then sorting, I also explained that you just can use sort. If you have free capacity, implement a partial sort. So that's the first part of the exercise sheet. And then you should play around with K and B and see how well they work. We will talk about the second exercise later when we talk about the second part. There are other ways to modify the score. You could also take the popularity of a movie into account, which you kind of already did for the first sheet, just by the way that the more popular movies are at the top. You could also, this is what I said. Oh, I don't have more. Okay. Okay. Yeah, here's more. No. What's not on the slide, I was expecting it on the slide. What's not on the slide is, but you probably don't want to do that for the sheet, is how close words occur to each other. You could also have information about position in a document. Yeah. Here I just mentioned taking the popularity into account. If you want to play around with it, go ahead, but you don't have to for the exercise sheet. Here are other methods which are beyond the scope of this lecture and this score. What the big search engines, of course, do is use click-through data. People search something, they click maybe on link number 3. Now Google knows, okay, not the first hit, but the third hit was actually obviously a good match, and they remember that. And then there is learning to rank, which I just very briefly list here, where you build a machine learning model to somehow do the ranking, and we will do stuff like that in the second part of the lecture. But this is just so that you know that there's also other stuff. Can you give, there's a question in the chat, can you give hints on finding good K and B without brute forcing? Actually, maybe ask this question again in the end, because it will be part of the second exercise, sort of, and it somehow belongs into the second part. Any question right now before we make a break? Okay, 5-minute break. See you again in 5 minutes. I'm assuming that people on Zoom can hear me again. We continue. So, okay, somehow the first sentence of this, why the lecture is called Ranking and Evaluation. Why evaluation? I mean, I should say a word about this, I guess. You have these formulas. Why this formula? Why not another formula? You can come up with so many heuristics and then, okay, this formula, which K should I take, which B should I take? You somehow have to make objective how well it works. And that's what evaluation is about. It's of course very important for any such framework. And so to evaluate something, you need a ground truth, like the ideal, what's true. And this is how a ground truth looks like for our setting, and we will have this in other settings too in future lectures. So for example, we have a query, matrix movies, and then we say somebody went and did the work. These, in this collection, these are the documents relevant for matrix movie. And let's say there are 4 matrix movies, 10, 582, 877, and 10,003. So this is now the ground truth. So if a search engine returns these 4 results, it's perfect. So you call this the ground truth, like the perfect result, and a set of such queries with their ground truth, you call it a benchmark, because it allows you to evaluate the performance, in this case the quality of such a system. We have built a benchmark for you, or Sebastian has built, and previous assistants have built a collection, and let's look at this. And you will see there are 2 collections, test and train. I will talk more about this later. Let's look at the training set, movies, benchmark, train. And it looks like this. So you have, it's actually a small file, but it's a lot of work. So you have, let's look at films shot in Spain. So we have a query, films shot in Spain, and now here we have the alleged ground truth. These films were all shot in Spain. And not only these films, but these are all the films shot in Spain. We have them here. And you see, let me maybe not do it like this, but like, I'm sorry, like this, that I see the whole list, yeah. Or, yeah, films where Dwayne Johnson was in the cast. So, and here I have the list of, so this is how a ground truth looks like. So a small file, but a lot of work. Yeah, and this is actually a very important part of research. So these kinds of, sometimes it can really advance a field if you have a high quality benchmark, but obviously it's a lot of work because you have to go to your collection, maybe it's a huge collection, and find all the relevant documents. How do you even do that? Different question. Now let's just assume we have such a benchmark, a ground truth. How do we evaluate our BM25 function or whatever function with certain parameters? That's what this part of the lecture is about. And let's start with some simple measures. Precision at K, and here's, let's just do it for an example. So now, and that's always the setting you have, I have my query, I have the ground truth, and now I have the ranked list of results. And at the end of this part, maybe it occurs to you already now, it's a bit strange, but let's just take it for granted as the moment. The ground truth is a set, the result is a ranked list. That's kind of strange. Why isn't the result list also a set, or why is the ground truth also a ranked list? But for now, let's just take it as it is. The ground truth is a set, so these are the relevant documents, and the result, search engine, always return a ranked list. Maybe you want to think about this if you have spare capacity. Why is the ground truth a set and the result is a ranked list? And now we want to say, okay, the search engine produced this result, how good is it with respect to this ground truth? And all the following slides will introduce different measures which somehow measure this. So let's first write on top of each document, this one here is relevant. No, I want relevant in green, I think. Yeah, this one is relevant. Let me write it like this. This is relevant. 566 is not. This one is relevant. And this one is also relevant. And 37 and 17, and these are not relevant. So let me just write it like this. Not relevant, not relevant, not relevant. Okay, and now, do we have anything else on this slide? Yeah, this will come in a second. P at 1 just says, when I look at the first one document, how many of these are relevant, and it's 100%. So if I just look at the top 1 ranked documents, if I look at the top 2 ranked documents, so now I'm looking at these 2 and I'm asking myself, how many of those are relevant? Which percentage of those are relevant? 50%, yeah, you got it. That's 50%. And let's continue. How many of the top 3 are relevant? What's the percentage? 33%, yeah. So it's 1/3, which is kind of 33 point something percent. What's P at 4? Yeah, it's 50% again. So it's not that the P at something goes down, right? Now I have a relevant one again here, and now it's 2 out of 4 which are relevant. So maybe to clarify, let me write that like this. Maybe let me quickly write it like this. I think it's a bit clearer. So this is 1 out of 1 is 100%. This is 1 out of 2, it's 50%. This is 1 out of 3, and let's not write something. This is 2 out of 4 is, yeah, let's write 33%. And the third one? It's 60%, exactly. So, and then there's a special measure which says P at R, where R is the, yeah, you shouldn't just know what it is, where R is just the number of relevant documents. So let's assume here we have 3 relevant documents, and then this one here is also called the P at, the P at R. Assuming that we have only 3 relevant documents overall here. So this is P at R. Okay, here's some more measures, which is based on the previous measure. Let's again take this one, and let's do the same thing again here. And let me just not write relevant or not relevant. Yeah, let me do it just like this. So this is, do I have the right color? Yes. So this was relevant. Which else was, this was relevant? I think it should be the same. 10 is relevant. And 877 is also somewhere in my list. So I'm looking for all the relevant ones, and this is not relevant, and this is not relevant. And I will just explain this by examples, and then at home you can try to really understand them, but these are very simple measures. Now I look at where are the relevant documents in my list. So I just give these, so this is the top ranked document, 1, 2, 3, 4, 5, and let's just say this is at position 40. So these numbers are just, so the first relevant one is at position 1, that's why I have a 1 here. The second relevant one in my list at position 4, that's why R2 is 4. The third relevant one is 5, R2 is 5. The fourth relevant ones, and that all the relevance ones I have here, is at position 40. And now, and in this example here, K is equal to 4. And now you tell me, and now I just compute the precision from the previous slides at each of these. You can compute the precision at every rank. I compute it at 1, 4, 5, and 40. And you tell me what it is. What's the precision at 1 for this list? 100%. That's 100% correct. What's the precision at 4? 50, yeah, 2 out of 4, that's correct. What's the precision at 5? 60, we already had that. What's the precision at 40? 10%, it's also correct. Yeah, it's 4 out of 40. Let's maybe just write that on top. So this was 1 out of 1, this was 2 out of 4, this was 3 out of 5, and this was 4 out of 40. And now the average precision, so you just look at where are my relevant documents, and you could compute the precision. Okay, here's my second relevant document, and until here I have a precision of 50%. And this tends to go down because it's, yeah, but it doesn't have to go down. And then the average precision is just, it's just the average of these 4 values. So that's, in this case, it's just, let's write it down, 100% plus 50% plus 60% plus 10% divided by 4, and that is? First the sum is 220% divided by 4, which is 55, yes. So, and one question here is, okay, if I have my search engine doesn't contain all the documents. It just contains documents which contain the keyword of the query. Maybe a relevant document was not even in the list, and then we just say this p-value is 0, which is like the same as saying it's very, very far back in the list. If it's very far, if you have a document here, if this is not at rank 40, but at rank 4 million, then this number will be basically 0. Now you have this so far was for a single query. Now in a benchmark, I showed you this, we have, let me show you here I have 28 queries. Now I can compute, for example, precision or whatever, average precision at 5 for this query, this query, this query. If I want to compute it for the whole benchmark, I just average it. And now here we have a measure for a query, which is an average of precisions of that query, why it's called average precision, but that's for a query. And now I want to compute the average over all queries in my benchmark. So it's like average precision. Average precision for this query and the average over all queries. And because there are 2 averages here, somebody had the ingenious idea of calling it mean in that case. So map, which is a very famous measure, is just the average of the average precision, and it's called the mean. Mean and average are really synonyms. So when you average over all queries, they use the word mean just to this average when you do it over a single query mean. So these are just the means, the averages over the whole collection. And thus you get a single number which tells you this is how well my search engine did for this benchmark. So you get a single number, which is of course dangerous because single numbers measuring something complex are always dangerous. And you should implement this for the exercise sheet. And all this stuff, very typical exam questions here. Like you can ask all kinds of interesting questions about this, like mathy questions also. So here 2 more, and yeah, we can take our time because they're basically the rest of the lecture will be 2 more. So these were very simple measures, right? So far, I mean precision, that's pretty simple. Now come 2 measures, yeah, which are a bit more involved, and you will understand why. But this one is also pretty easy actually. Let me see, is this 1 slide or 2 slides? Ah, there's an example. Okay. Here's a setting that you often have. You have a query, and so far we just had relevant or not relevant, but very frequently you say, yeah, that's kind of relevant, and this is very relevant. So you have shades of relevance, which means, yeah, in this case I have 3 shades of relevance, and you will see an example in a second. And here's a formula And I will just do it by an example on the next slide. So here's an example, and we will go back to the formula on the previous slide. So here we have a search engine. Of course, the search engine does not know what's relevant or not relevant, and it returned these results. A relevant document at the top. The second document it returned was not relevant. The third document it returned was very relevant. The fourth one was relevant. The fifth one was not relevant. And now let's look what the formula on the previous slide says. Now we somehow compute. Now I go back like this. The formula does the following. It computes this sum here, and for now we will just compute it without understanding what it means. Let's just compute it. So I just sum up the relevance values, which are 0, 1, or 2, depending on how relevant, and I divide by the position, by the log of the position, plus 1. Let's just do it. And so this is, and then by doing the example it will be clear. So this is, and I do it until position 5, so it's always add something. Until when do I do it? So this is the first relevance value, which is 1 over, and now I do the position, which is log 2 of 2. For the first position it's 2. Log 2 of 2. Then this is the, and maybe to clarify this, let me write this number here in green, to clarify that it's indeed that number. Now the second one, I don't really have to add it up because it's a 0, but I still write it here so that it's clear. 0 log 2 of 3. This now just goes up. Now comes a 2. I know it's not the same green, but I hope you can see the connection anyway. This is now log 2 of 4 plus another, the 1 here, that's this relevance value, 1 of, oh no, this is not correct. Log 2 of 5 plus, and then, yeah, let's also write this. And maybe someone of you can just compute this sum. This is not something you can do in your head because logarithms of non-powers of 2 tend to be funny numbers. So can someone compute it? So actually we can simplify it a little bit. It's 1 over log 2 of 2. This is 1. So maybe let's do this here. Now I need a little bit of space there, so I should erase this. So this is equal to 1 plus log 2 of 4 is 2, 2 over 2 is 1, 1 plus 1 plus, and here we have 1 over log 2 of 5. So this should be something like 2 point something, and who can tell me what it is? 1 over, I'm sure you are all log 2 of 5, let's see. Okay, it's this 1 over, so it's 0.43. This is 0.43 something, so that's 0.43 something. You will understand in a second why we're doing it like this. Let's maybe, now we have a little problem here. We get a number 2.43, and the question is this good or bad? I mean, usually you want to measure which is somehow, if it's bad, it's 0, if it's good, it's 1, or the other way around, you know what the range is. Here we don't really know the range. So what we are doing, we are also computing like the best version of this. And now it will also become clearer why we'll do the logarithm, the thing in the denominator. So what would be the best ranking here? Which one should be at the top here, if it's in the best case? The very relevant one. So in the best case, it should look like this. I have the very relevant one here, the other two relevant ones next, and then I have the not relevant ones here. And now let's compute that number. And now this becomes 2 over 1 over 1 over, and I leave out the zeros because they don't add anything. So that's now 2 over log 2 of 2 plus 1 over log 2 of 3 plus 1 over log 2 of 4. And you see, without even computing it, this denominator becomes smaller and smaller. So that's the idea. That's why it's discounted. Now you understand the discounted. If I get a very relevant one further back in the list, yes, there's a 2 in the numerator, but the number in the denominator will get smaller. It doesn't get smaller very fast because of the logarithm, but it does get smaller. Whereas a 2 in the beginning is really good because log 2 of 2 is 1. This log 2 of 4 is already 2, gets divided by 2. This is much better. So that's the idea of discounted. Yes, it's good to have a relevant document, but it's much better to have it at the front. And a very relevant one at the front is really good. So it's actually a simple idea. So here I have 2 over 1, that's 1, and this is 2 plus. This we have to Google, log 2 of 3, and this log 2 of 4 is 4, so that's 1/2. And that's, let's just Google it, 2.5 plus, or it's 1 over, no, that was wrong, log 2 of 3 is 0.63, so this is 0.63, let's just 0.63 something, so this whole thing is 3.13. And now, oh my, now, yeah, I knew this was coming. Okay, that's very bad. What do I do now? I think I will just write it again. That's fast. 0.63. You have to remember 0.63. So this is 2 plus 1 over log 2 of 3 plus 0.5, which is 3.13 dot dot. And now we know, okay, this is the value we got. This is the best value. Let's just divide this by that. And then I get a number between 0 and 1. So this is now, and let me not write the real terms, but just the approximation. So this is 2.43 something divided by 3.13 something is equal to, and let's maybe write to compute it here. So that was 2 divided by log 2 of 5. It was this number. Divided by 2.5 plus 1 over log 2 of 3, right? Think so. Yeah. So apparently 0.7763. Which is 78%. So kind of, yeah, you get the idea. So this, yeah, not bad. Some relevant ones at the top. The very relevant one at position 3 could have been better. The optimal value of this measure would have been this, and we reached 78% of the optimum measure. So that's a measure you will also find very frequently. 2.43. People in the chat are helping with the computation. Any question about discounted cumulative gain? Was it clear enough? These questions about these measures are super typical in the exam. You will certainly get questions about this. Not only, let me just explain, there will of course be questions, or might be questions about, here's an example, do it, but there are also Yeah, you could also ask, is the DCG at 5 always bounded by 1? No, it's not bounded by 1. It can be larger than 1, right? Only but the NDCG, that's a number between 0 and 1. So there are some things to understand here, and you can ask simple math questions about it. And here's another one that's also nice. So it's the last measure we do today, so just concentrate for one last time, but it's also very important. And the motivation is the following. If you do competitions, and they are very frequent, they have always been very frequent and they still are. Now here for the exercise sheet, Sebastian and others spend a lot of time creating this benchmark. That's a lot of work, and so we don't. Films shot in Spain, how do you do it? Yeah, there are different ways to do it, but you somehow have to go to the collection and find all the films shot in Spain. And this is a collection with 100-something thousand documents. If you have a collection with billions of documents, you can't do that. You can't have a complete ground truth. That's very typical, very normal. But still you want to do a competition. You want to compare systems. So you have the situation where you have some relevant judgments, but not others. For most of the documents, you just don't know whether they are relevant or not. So now what you do, you have participants in your competitions, and they have their search engines, and hopefully they are good search engines, and each of the search engines will give you results, maybe 100 results. And now maybe you have 10 people participating in your competition. You just look at their search engine and see which results they return. And now you just take, let's say, the top 10 results from each search engine, and now you just judge those. You just go over those manually and say relevant, not relevant, relevant, not relevant. Now at least you get some relevance judgment. You have different search engines, and you just look at their top results and you judge those. This approach is called pooling, but this is just the motivation for this measure. And now, again, and you will see this a lot with all these measures, you get a formula thrown at you. Here's the formula, 1 over R, sum DRR1 minus NR. Right, you have seen it for NDCG, you have seen it for BM25, there's a formula. And when you see it for the first time, you have no idea what it means. And the whole point of this lecture and of this is to actually you can understand very well what it means. And we will do that with the example now in a second. So let's not spend too much time on this slide and formula. It's just there for your reference. Let's maybe look at what are the entities that are used in this formula, because they can be understood well. R is, and that's actually, so some of the documents were looked at, and R is just a set of documents where somebody looked at and said, that's relevant. That's easy to understand. So we have a set of relevant documents. We have a set of non-relevant documents. Somebody looked at them and said, this is not relevant. It was returned by one of the engines in the competition, not relevant. Now we are talking about particular engine. We always want to judge a certain result list, like with the previous measure. That's RR. We look at, now this is what our search engine returned, and we will talk about this in a second. So here's an example. This is how it looks like. It's always best to understand these with an example, but then you also have to understand them in the abstract. So our search engine returned this, and now we have to say, how good is this? And we are in the following situation. We know for some documents they are not relevant. They were judged. For some we know they are relevant, so we have no grading here. And for some we just don't know. Maybe relevant, maybe not. Nobody judged them because of what I just explained. And we also know, so this is what our search engine returned. We know there's one more relevant document which it did not return. That's not good, but that's just how it is. So this, of course, should give a penalty. And there are 10 more non-relevant documents which it also did not return. So that's what we know, and now let's look at the numbers. And actually you don't have to remember the formula, I will just explain it again. And it's actually very simple and also intuitive. So RR is just the relevant documents which we returned. It's the set of relevant documents which we returned, which means in this case it's number 3 and number 8. Okay, then we have the number of relevant documents overall that were judged. For this particular query, 3 relevant documents were found. There may be more, but only so many were judged, so this is 3. How many non-relevant documents were found? Usually there are more, so also in this example, 1, 2, 3, 10 more, so it's 13. For some reason you take the minimum of the 2, you can't understand this at this point. Let's just take it for granted that we should compute the minimum, and it's 3. These 2 numbers, I didn't talk about them yet, but they are also very easy to understand, also in the context of this. NR at 3, you can't really compute the precision now, right? I mean, before we said, okay, let's look at the top 3, how many of them are relevant? Well, you don't know whether that's relevant or not. But what you can do is how many non-relevant ones come before these relevant ones. This you can do. And this is what we do here. And we can say, here's a relevant one, and 1 not relevant one comes before this, which is already not good, right? You shouldn't have not relevant ones come before relevant ones. And that's just what this counts, just how many non-relevant ones come before it. So it's actually very simple. So this is just 1. And you will see on the previous slide that what we actually computed was this here, divided by this minimum thing here, and this is then 2 over 3. So we just take 1 minus this divided by 3, because kind of, let's just do it for this one. So number 8, how many non-relevant documents become before the number 8? 3, yes, it's 3. And now we have NR number 8 divided by this minimum. And you may wonder why the minimum. I have a slide on this. I will explain it in a second, and that's 0. So even if you didn't understand everything yet, you can understand a few things. So we look at each relevant documents and we give each a score. So if we have a document and there's no relevant one before it, it will get a score of 1, right? We don't have this here. The first relevant one, this has 1 non-relevant one before it, which is already not bad, so we give it a score of 2 over 3. And here we have 1, there are only 3 relevant documents overall, and this has 3 non-relevant documents before it. That already gets a score of 0, and it only gets worse when you go down. And now bpref is just, you look at all the relevant ones, and you just take the average of these. That's it. So it's actually, it's 2/3 plus 0, but you also take into account those which are not even in your list, which is kind of similar to what we did earlier. So there's a third one which is not in the list, and being not in the list is like being very far down with all the non-relevant ones coming before it. Divided by 3, which is there anything else on this slide? No. It's 2 over 9. 2 over 9. Let's see your computation in the head skill. What percentage is 2 over 9? It's actually, what? 28? 22, I agree. 1 over 9 is 11, right? 22%, 22.2, and so on. And I think by this example, a few things already became clearer. Let's go. Now this formula already lost some of its terror. So actually what you have here And now you can understand also what I wrote here. But that's the typical way to understand something. An example, try to understand the example, then go back to the abstract. A score based on how many judged none come before it. That's this part, right? For each relevant document, we compute a score based on how many non-relevant ones come before it. That's what we did here. For this one, okay, one non-relevant came before it, got a score of 2/3. For this one, 3 came before it, got a score of 0. So that's the scores you compute, and then you just do it for all the relevant ones in your list, and then you divide by the number of relevant. It's just the average of these scores. It's actually a very simple formula once you understood it, but then you see it for the first time, it's like, what? And now there are 2 questions, and I have a slide on this. I think it's easy to understand modulo 2 questions. Why do we have the minimum here? Why don't we just divide by n? That would be more natural, right? You have number of not relevant ones coming before it. Why not just divide by n? I mean, there are at most 13 non-relevant documents. If I have just 1 coming before it, why not 1/13, but 1/3? And this sum is over RR, but I divide by, so it's just 2 relevant documents in our example in the list, but I divide by 3. Why not divide by 2? And this is something, let me only hint at it here, but it's something you have to, I mean, you absolutely have to think about it yourself at home to really understand it. And this gives you all the, I think, everything you need to be able to think about it. Why this number and not this number? And here you also have typical exam questions hidden, which also show you the kind of math which you're supposed to understand. It's not very deep, but still math. First, when you divide by the minimum of something, and this is supposed to be a number in the range 0 or 1, you should verify that this number is indeed, it's smaller than R, and it's smaller than N. It's smaller than both of them. And I leave that to you. This one is obvious, because it counts the number of non-relevant documents coming before that document, and there are only so many non-relevant ones. And this is just, by the way, how it's defined. You can see it 2 slides earlier. So this number is actually, if you divide it by this, it's between 0 and 1, which is what you want. So this is in the range 0 of 1, and then you take 1 minus this, so that 1 becomes good and 0 becomes bad. And then note, by taking the minimum with R, this is what you do. I have only 3 relevant documents, and as soon as I have 3 non-relevant ones becoming before it, I already say, okay, that's bad. That's just a decision this measure makes, right? So it's kind of, this minimum with R is making it harder. So, right, this would be an exam question, for example. Does the minimum with R make it harder to get a better value or make it easier? It makes it harder, because now just 3 not relevant ones are enough, and you already get a score of 0. Which just kind of makes sense, right? It's I have 3 not relevant ones coming before the relevant ones. That's bad. I don't want that. Given that I haven't even found all the relevant ones. So yeah, taking the minimum makes it harder to achieve a good BPref score. It's just a decision by the makers of this score. And then why 1/R? That's actually easy. I mean, that's basically what we did here. I have these 2 relevant ones in our list. One got a score of 2/3, one a score of 0. Now I could just take the average of these 2. Right? 2/3 plus 0 over 2 is 1/3. But there's a third one which my engine didn't even return. I mean, that's not fair not to take this into account. I should handle it as if it was at the very bottom of my list. And if you think about it, this is exactly, and let me find this, it's not so easy to find, but I will manage the AP slide. Yeah, it's exactly what we did here, right? I mean, it wouldn't be fair if my search engine, take this example, my search engine just returns one document and it's relevant. But there are 4 relevant documents. I shouldn't give it a score of 100%, right? I mean, yes, it returned one relevant document at number 1, but the other 3 it just completely forgot. It didn't even return them. I shouldn't give this engine a 100% score. It will get a 25% score. It got the one document right, that's the 100%, and the others are nowhere to be seen. It's 0 plus 0 plus 0 divided by 4. I should punish that, and that's what all these measures do. If a relevant document is not even in my list, it counts as 0. And that's the reason. That's why I have the plus 0 divided by 3 here. Not being in the list is like being very, very far down. And this measure also does that. And given all that now, I think this formula is actually pretty easy to understand. I mean, you just compute this score per relevant document, which just counts how many non-relevant ones come before it, and you take the average of those over all relevant ones. It's actually a simple measure, but when you see it for the first time, it looks crazy. So, what would happen? There's a good question. What would happen if number 6 was also relevant? Wouldn't NR be negative? That's a good number. Somebody said this can become, it absolutely shouldn't become negative. Good question. Here's a detail. I kind of hinted at it in one of the sentences I said. NR is just, it's capped at R. It doesn't become worse than that. Docs from the R top-ranked non-relevant ones. So I kind of stop. Yeah, I know that you meant not relevant. So it's a very valid question. So let's assume number 6 is also not relevant. Now I would have 4 non-relevant ones before it. Does it mean, so this would be 4? Does this mean this measure now becomes negative? No, because I only count until R. So if I have 3 relevant ones, I just count not. Now it's already 0, it doesn't become less. And that's what's written here. Docs from the R, from the top-ranked non-relevant ones. I only consider the first 3 non-relevant ones. And the only reason for that is so that that score doesn't become negative. It's actually just for that reason. It's a very good question. But yeah, that's the way to understand these formulas. Really just understand everything. Why is that so? And then you see, okay, that's just the reason for that. Some general remarks, then back to the exercise sheet, and then we are done. Now I think is the time to go to the exercise sheet once more. What will be the second part of the exercise sheet? So you implement BM25 in the way we explained in the first part. Now you get these benchmarks, and now you should compute, okay, my search engine with this BM25, with this choice of parameters, maybe I implemented some other heuristics as well. How good is it on these benchmarks? So you should compute these precision at K, average precision. So from the first part of the lecture, P at K and AP, no discounted average here, but the simple measures. And then you should just write an evaluation script. That's very typical in research. You have a benchmark, you have to write an evaluation script which actually computes these measures. And now comes the third exercise, which kind of mimics competition. Now you have your code and you have your benchmark, and now you want to improve your result. So now you want to, and that was the first question in the chat today, how do I pick B and K? Now you play around. Let me make B a little smaller, larger, K. You also have some heuristics. Maybe you say, let me take the popularity into account. And then you see, does it help or not? And for that, now it's very important that we have 2 data sets here. One is called train and one is called test. And now listen carefully, because that's super important, not only for for this kind of queries documents, but for every competition on this kind. And let's look at them first. This is how train looks like, 28 films with their relevant documents. And this is how test looks like, also 28 films, queries with their ground truth. But it's different queries. They are kind of a similar kind, but different. So here we have the first one is James Bond movies with Daniel Craig. Here we have movies with music composed by Howard Shore. Different queries. Why is that important? Well, what you could do is, and it's kind of trivial, you take one of these sets and now you work hours or days just to improve the result on this set. And think about it, it's trivial. Actually, one way you could do it to write in your code, if query equals movies with music composed by Howard Shore, then output 10, 11, 13. Yeah, that would be the crassest form of overfitting. You just, if it's this query, then output this. Now you have a perfect score. You just implemented a program that outputs the ground truth. You can even input the input file. I mean, it doesn't make sense, right? You get a perfect score on your training set, but it will only work for your training set. So that's called overfitting. Now this was a crass example of overfitting. Let's just leave it open. We're done in a... Or maybe close it for the... I think we won't suffocate. It's actually below what it was at the beginning. It's just 5 more minutes. I think it will. Yeah, that's the reason. Thank you. So that's what's a crass form of overfitting, but the very, very important message here, that you unconsciously do something similar when you look at this set and then you say, now I understand, I should pick B larger. You think you understand something about the general problem and you're playing around with your parameter and you're putting an if in your code here or there. You're doing 100 things which you think they are actually good for the problem in general, but actually you're overfitting to the training set because you only look at these queries all the time. Now I understand. When the query contains Leo DiCaprio, I should do this. Now I understand. So you think you're doing something general, but maybe it's not so general. Maybe you are tuned too much to that training data set. And how do you solve that problem? How do you deal with that bias? Well, that's the way to do it. That's why you have 2 sets. You can do all that work on the training data set. Here, you can do as much overfitting as you like on that training data set, and then after you're done, you say, okay, now I'm done. This is my code. I take B equals 0.54. I take K equals 1.31. Now I'm done, and now it's evaluated on this data set. That's the point. That's how it's done in all the competitions. You do all your training and everything on this data set, and now it's evaluated on this one. And of course, if you have overfitted a lot, it will be good here, but bad here. What counts is the result here. But you had the opportunity to train on something meaningful. So that's why we do that. Now, of course, you can cheat. I mean, it's stupid if you do. I mean, that's not the point of the exercise. You shouldn't. The point is, and in real competitions, you don't get the test data set, of course, right? In real competitions, you will only get this one, and then you commit it, and then the people from the commission will or they have set up a system which does this. Here we give you both data sets, but we ask you to do all your tuning only on the train data set. Do not even look at this data set. Do not even look at it. Forget about its existence. And then when you're done with the tuning, just once, run it on this set and see how good it is. So that's the way how to do it. And you learn an important lesson here, how it's done for these competitions. Okay. And now the final point, I announced this earlier, and then we're done, so that's the exercise sheet. And maybe somebody has an idea. Let me just go back, and it's the final thought, but it's an interesting one. Isn't it weird that the ground truth is a set, but our search engine returns ranked lists? This is weird, right? This, if you think about it, at least I find it weird. So the ground truth is a set. Here the 5, why, and this gives rise to a number of questions. So why does our search engine not also output a set? Why do search engine not say, here are the 5 relevant movies? Why does it output a ranked list? And I mean, you can say something if you want, but I can also, does anybody want to say something? At least these are questions to think about. Why is the ground truth a set, but you output a ranked list? Well, the point is, if you output a set, if you want to output a set, Google would have to say, okay, I have internally it does this ranked list thing, and now it has to say, okay, I'm supposed to return a set. Let me just cut off here and just give the user the first 6. Well, that's dangerous. Why not? Maybe the 7th one was the good one. Why not give them the ranked list? Then they have the opportunity. You empower the user to scroll further down. Most of them won't, but that's the reason why search engines return ranked lists, because otherwise they would have to cut it off. Okay, so it's natural to have ranked lists. So why isn't our ground truth also a ranked list? Now our ground truth was here 5 relevant documents. Well, if you ask for the Matrix movies, it's kind of hard to put them in an order. I mean, you can say these are the 4 Matrix movies, but yeah, you can't really give them an order. Maybe you can say, yeah, this is the best one or the first one, but you don't really have an order. The reason that you have ranking in your result list is what I just explained, but actually the relevant documents often don't have an order. It's just a set. And here's the 3rd one, okay. So why don't you evaluate the scores? Like, here's my ground truth, this movie should get this score, and your search engine also computes scores, and now you compare how well do the scores match. Well, that also doesn't work because the scores really don't mean that much. We only compute scores to rank the documents. Let me go back one more time. These scores, I mean the absolute values of the scores, this 30 or here, this value doesn't mean much. The only reason we compute these scores is so that we can rank the documents later. I mean, there are problems where these are called regression problems, where the goal is actually to compute a score, but not here. That's it for today. So is there any question at this point? Okay, there's one question, yes? Yeah, sure.
If I didn't submit first exercise, I can submit second.
Oh yeah, absolutely. It's free. Submission of exercises is free. You can decide from week to week whether you want to submit something or not. There's no need to communicate your strategy or anything. You can just decide that on a weekly basis. And you are welcome to. Any other question? Okay, so have fun with the sheet. See you again next week. Bye-bye.